Hello everybody. Welcome to this probability video. The topic for this video today is the idea of something we call independence in probability, and I'm also going to teach you about something called the multiplication rule. So you've already seen the video about the addition rule. This one is multiplication rule. Okay. The addition rule deals with OR probabilities. The multiplication rule deals a little bit more with and probabilities and this idea of independence. Okay, so we're actually going to start this video with a little like simulation, a game, an idea, so that I can kind of illustrate to you what independence actually is. Okay, so we're going to pretend that we are playing a game. If you've ever gone to one of those carnivals, you know how they have like those carnival games that you can play. Right, so there are 40 cards in this game. 10 of them are blue, 10 are green, 10 are red, and 10 are yellow. And then there's a number 1 through 10 on each set of cards, like each set of colored cards. So there's like 1 blue, 2 blue, 3 blue, 1 red, 2 red, 3 red, etc. Okay, so we're going to try to calculate some probabilities here. In this game, we're just going to pick a card at random, and if the card is an 8, a 9, or a 10, then you win a prize. It does not matter what color it is, as long as it's an 8, a 9, or a 10. Okay, so I have all the options laid out for you on the right side of the screen, right? So there's blue cards, 1 through 10, green, 1 through 10, red, and yellow, 1 through 10. So let's ask ourselves, okay, what's the probability that I win a prize here? So I know that I can win a prize by getting any of these cards right here. Those are my 8s, my 9s, and my 10s. Remember, it doesn't matter what color it is. So there's 12 cards here out of 40 total that would give me a chance to win my prize here. And let's reduce that fraction because it's going to help us a little later. So my common factor here is 4. I can divide both of these numbers, 12 and 40, by 4. So 12 divided by 4 is 3. And 40 divided by 4 is 10. So I've got a 30% chance of winning the game here. Okay, so next, we're at the carnival, right? And the dealer, right, or the carny, the person running the game, is going to pick a card for you. So you don't get to pick a card. They're going to pick the card for you. And they tell you that the card is blue, but they don't tell you that they don't tell you what the number is on the card. So we want to figure out, okay, well, now what's the probability that I win? So this is a given probability, right? I gave you a restriction. We were told that the card was blue. So these are the only cards that could be drawn, right? I know that the card is blue, but I still can only win if I draw an 8, a 9, or a 10. So let's figure this out, right? So now in my blue category, there's only 3 numbers that will give me a win, right? An 8, a 9, and a 10. And then there's 10 numbers total, right? Because remember, this is a conditional probability, so there's a restriction here, okay? And what I'm hoping that you notice is that these probabilities right here are the same. Okay, and what this actual probability is that we found, this is the probability that we win given that I already know that the card is blue. Okay, and that's the answer here to this part C. That's the probability notation. Okay, so in our scenario here, knowing what color the card was didn't change my outcome. It did not change me knowing or the chances of me winning the game here. That is exactly what independence is in probability. So the actual full geometric definition of independence is that 2 events are independent if one event will happen whether or not the other event happens, right? So in this scenario with the card game, my 2 events are winning the game and drawing a blue card. So this first one is just the probability that I win a prize. Okay. And then in the second one, I introduced a restriction and I told you that the card was blue, but that did not change the outcome, right? Me knowing that the card was blue didn't really matter. Okay. So this event occurring, the blue restriction being put on there, did not change the chance that I was going to win. Okay. So that is what independence is. And if you are actually talking about independence and looking at the, let me change my color here, and you're looking at the definition of it, this is the geometric definition of independence right here. Two events, A and B, are independent if probability of A given B is equal to probability of A. Right? And I'm right down here, okay? Meaning that me introducing this extra restriction, adding the B, didn't change the fact that the first event was going to happen. Didn't change the probability that that was going to happen. You really only need to know this one right here. The second one is exactly the same, just with the letters switched. Okay, so I'm going to do another problem for you here and show you what it'll look like. Whoops, I went a little too far here. Okay, I want to show you what it'll look like here when things are independent and when things are not independent. Okay, so let's look at number 2 here. So in this problem, I'm rolling a dice, basically, right? But instead of little dots, there's numbers on them, like 1, 2, 3, 4, 5, and 6. Okay, and I have 3 events possible here. So E is the event that I get an even number. So let's figure out what that probability is. From 1 through 6, there's 3 numbers that are even, 2, 4, and 6. So I have 3 out of 6 is my probability here. Okay. F is the event that the cube shows a number greater than 2. Okay, so from 1 through 6, there are 4 numbers that are greater than 2, right? 3, 4, 5, and 6. So that's 4 out of 6 is my probability there. Okay, and I'm actually going to reduce these fractions a little bit just so that you can see what's happening here. Okay, so 3 out of 6 reduces to 1/2. Oops, sorry, everybody. My computer's being wonky. So this reduces to 1/2. 4 out of 6 reduces to 2/3. Okay, and then my last one here, G, is the event that the cube shows a number greater than 3. So there's 3 options there, right? 4, 5, and 6. So this is 3 out of 6, which again reduces to 1/2. Okay, so let's look at these 3 parts of this problem right here. So probability of E, we found it's this right here. Okay, so probability of E is 3 out of 6, which is equal to 1/2. Okay. Part B says find probability of E given F. Okay, so I know that that F has happened. So I know that the number that I rolled is greater than 2. So there are 4 numbers that are greater than 2, right? And then with the definition of conditional, remember we're looking for E and F divided by F, right? So F, there's 4 options for F, which is why it's down there on the bottom of the numerator, that number 4. And then we need to think, okay, E and F is both of these events happening together. So how many even numbers are there that are greater than 2? Well, there's 4 and there's 6, right? So 2 values there, 2 possible values. So I get 2 out of 4 here. And if I reduce this, I get 1/2. So notice that I have the same number here, and here. So me adding the extra restriction or giving you extra information that the dice or the cube that you rolled had a number greater than 2 didn't change the probability that I would get an even number. So these are independent because the probabilities here are the same. Okay, let's test it with E given G. I think we're going to get a different result here. Okay, so again, if I'm finding probability of E given G, that's E and G divided by G. Okay, that's the definition of conditional probability. That's how you find it. So let's look back at G. So event G is probability that cube shows a number greater than 3. So there are only 3 numbers on this dice that are greater than 3. Okay. And then both of those events happening together is the even numbers that are greater than 3. And there's 2 of those numbers, right? 4 and 6, right? So that's 2 out of 3. 2 out of 3 and 1 out of half and 1 out of 2, are not equal to each other. Okay, so that means that these are not independent. Okay, so me adding this extra restriction changed the probability of event E. So that means those are not independent, right? So the extra restriction impacted or changed the probability of event E. Introducing the extra thing actually increased the probability that I would roll an even number. Having that extra information changed it. Okay, so key thing to take away from this here is that if you add the restriction and you still get the same probability, they are independent. Those 2 events are not going to affect each other. But if the probability changes, then that restriction affected the probability of the first event. Okay, so let me clear my screen here because we're going to try a couple of these with some Venn diagrams, actually. Okay, and we're going to look into this this idea of the multiplication rule, and I'm going to show you how to use that because the definition of independence can be kind of tricky to figure out. But there's another way that you can figure out if 2 events are independent, and that's called the multiplication rule. So if we look at this first problem on the top of this page, number 3, we're talking about the intersection of people who do strenuous exercise and people who walk for pleasure. So we're talking about exercise and people that do neither of those things. So what I would love for you to do is pause the video really quickly and see if you can fill in the Venn diagram with, I'm going to put E over here. So there's my strenuous exercise. And then I'm going to put W over here. That's my walk for pleasure. Obviously, this is the middle. And then really this should be in a big box, right? Because I have that 21% that don't do either of those, which would go out here. Okay, so I'm going to give you a minute. See if you can fill in every blank space in the Venn diagram, which the middle is a little tricky. And the hint I'm going to give you is that you need the addition rule, which we learned in the last video. So that's, that would be E or F or W, equals E plus W minus E and W. You're going to have to do some solving. All right. Okay. So go ahead and pause the video, see if you can figure that out, and I'll see you in a second. Okay. So I figured that you may have gotten about this far, and then you may have gotten a little stuck to figure out what this middle part is. So I wrote something out to help you. Okay. So what I need to figure out is this middle part right here, this and probability, this one right here. But in order to do that, I need to know these other 3 things. I can't have 2 variables when you only have 1 equation. Okay. So I know from the problem that 21% of people do neither of those things, which is why 0.21 is out in the bottom right-hand corner. I know that 68% total is in that E circle and 50% total is in the W circle. So that's probability of E and probability of W. Now, one thing that I hope you remember from Miss L's video is that the OR probabilities is everything inside of the Venn diagram, inside of the circle. So it's these three values, these three blanks right here. So I know all together this has to be 0.79 or 79%, right? Because 79 plus 21 gives you 100%. Remember, these four numbers, 1, 2, 3, 4, have to add up to 1 or 100%. Okay, so this 0.79 is E or W. So if I do a little bit of math here and do some solving, I can add these two values together. And when I do that and solve for E and W, so when I add these two together, I get 1.18, and then I need to do some subtraction. So if I do 1.18 and then I do minus 0.79, what you get here is 0.39. Okay, so I have 0.39 in the middle there. So what that means for these other two blanks is I need to then do some subtraction from the totals. So for E, I have 0.68 minus 0.39, okay, and that is oh, sorry guys. That is 0.29. Okay, and then I can do the same thing over here for W. So I know that 0.39 and this blank have to add up to 50.1.5. So 0.11 or 11% is what's going to give me that value. Okay, so now we have all of the information in the Venn diagram. So let's see if we can use it to figure out if these two events are independent. Okay, so based on the definition of independence, I want to check, is the probability of, say, E equal to the probability of E given W? So I'm going to add in the restriction. So probability of E, I already know that value is 0.68. And then I want to know, is that equal to the probability of E given W? Okay, so E given W, remember, is what's the probability of, so W is my restrictor category. So I have 0.5 on the bottom, and then E and W is this, right, that they share. So 0.39, and I have to figure out what that is. So I'm going to plug into my calculator and do 0.39 divided by 0.5. And when I do that, I got to put a question mark here, I get 0.78. Okay, so I get these two values that are different, which means these are not independent. Okay, and you're probably going, oh my dear Lord, that was a lot of work. Okay, I get it. So there's another way that's a little bit simpler, called the multiplication rule, that you can use if you don't want to use the definition of independence, which is what I used right here. So this right here that I'm boxing for you in orange, this is the multiplication rule. Okay, so two events that are independent, if you know that two events are independent, then you can multiply their probabilities together and get the and probability. Now, again, this only works if they're independent. So if you know the and probability, So like up here, we know that the and probability is 0.39, right? We calculated that. And then if I check to see if they're independent, I can do that by multiplying the individual probabilities together. So this one would be like 0.68, and this one would be 0.5. And when I multiply 0.68 and 0.5, when I multiply those together, I actually get 0.34. So see how I get different numbers, right? This one was 0.39, this one's 0.34. So that means these are not independent. Okay. So give me a second to clear my screen. And, well, actually, no. Here's what I want you to do. There's two more problems here that deal with independence and the multiplication rule. So now that you know the multiplication rule, you can do these independence problems two ways. You can either check them using the definition method, which is what I did in number 3 right here, or you can use the multiplication rule to check to see if events are independent. Okay. And then one thing I do want to note for you is that if you are told in the problem that the events are independent, then you can use this formula right here to figure out something that you don't know, right? Say you didn't know the and probability, but you knew these two probabilities, A and B, and you knew they were independent, then that would mean you could do some multiplication. Okay. So with all of that, I want you to try number 4 and number 5. So go ahead and pause the video, pick whichever method makes the most sense to you and give it a try. I would advise, just to kind of get your head on straight, if you need to, for number 4, to draw yourself a Venn diagram because they didn't give you one. Okay. So try number 4 and number 5 and then check your answers with me when you're done. All right, welcome back. So I had to change my screen a little bit so that I could draw some of these things a little bit better for you. So let's take a look at this question number 4. Okay, you don't actually technically need a Venn diagram for this one, but I'm going to draw one just to help you out a little bit. You can plug things directly into the formula if you want. Okay, so I know that the probability at this school that a kid has a grade over 90 is 0.29. Probability that they live in the southern part of town is 0.42. And I also know that these events are independent. So if I sketch myself a really, really quick Venn diagram here, if this is G and this is S right here, I know that the G probability is 0.29. And I know that the S probability is 0.42. So this first question is, I want to know the and probability. So I'm trying to find this, but I know this and this. So let's do some multiplication. So probability of G and S is equal to probability of G, which is 0.29, times probability of S, which is 0.42, right? And once you're at that point, you can plug those things directly into your calculator, which I'm doing right now. So when you multiply these together in your calculator, you get 0.122, and I'm going to round up because the decimal goes a little bit further, but you can round here. 2 decimal places or even so 3 decimal places or 2 is fine. So this probability right here, the and probability, is 0.122. Okay. So a little bit easier, right, than using the given definition. It's really difficult to use the given definition here because of the information that you got at the start of the problem. A lot quicker, a lot easier, which is why I like the multiplication rule. Okay. Part B says, what's the probability? What is the or probability here? So in order to do that, I actually need the addition rule, which I gave a note to you here on. So remember, that would be the or probability. So G or S is So remember, you add the two individual probabilities together. So probability of G plus probability of S. And then you have to subtract what they have in common. So probability of G and S, which we just found. So we actually have all of the information that we need for this problem, right? So G was 0.29 plus 0.42 and then minus 0.122. Okay. And I'm going to be honest, once you get here, you don't really want to have to do this like by hand. It's much easier to do in a calculator. Like you might as well do it in a calculator if you can. It just makes life a lot easier. Because like those numbers are kind of big and that's a pain, right? I'd rather not have to deal with that. So when you do all of this in your calculator, and sorry, I was over here doing it in my calculator because I'm a bad math teacher and I didn't do it beforehand when I had the video paused. Okay, so 0.29 plus 0.42 is 0.71, and then you subtract 0.122 from that, and you get 0.588. Okay, and that's it. Okay, so that's how you would find that OR probability. Much easier than some of the ones we did up ahead. Okay, last one here. I'm hoping that you tried number 5 as well. Okay, so my last one is asking, are these events independent? So what I'm trying to see is, does this formula work how it is supposed to? So let's check it. So probability of A and B is right here, 0.24. So I'm checking 0.24. Does that equal, question mark, A times B? So 0.4 times 0.6, okay? And 0.4 times 0.6 is 0.24. So those are equal, so these are independent. And it's as simple as that, right? So that's why I like the multiplication rule. It's a little bit easier to deal with than the actual definition. But if you like the definition, go ahead and use that. Both of them will work. It doesn't matter which you use as long as you use them correctly. Okay, so key thing from this video, a couple key things to remember are independence is when adding an extra restriction, so adding a given probability when that does not change the outcome of the original event. So adding a restriction doesn't change the outcome of the original event. That's the definition way to figure out independence problems. And then we have the multiplication rule, which is that if you multiply the two probabilities of the individual events together, you will get the and probability, the intersection, but that only works when they are independent. All right. And that's the multiplication rule method.